Actually not. I'm just in the WebEx right now. Normally you can hear, oh, sorry. I will just join the event right now, so you can see me. Test.
Boa tarde a todos de novo. Antes de começar, queria... So we got the camera. I'd like to check your mic.
Yes, you can hear me. Is the gain good for you? Hello? Yeah? Can you hear me? Can you hear me?
Okay. Perfect.
Super.
So I'd like to test your
Oh. So what do you want to check? Sorry. Yep. Can I share also the presentation like that, for example, like during the using the camera? Yeah, super. Dedans. Oh. It's cut a little bit. Okay. Maybe I can. Okay. Now it should be better. Super. No problem. Thank you very much. Thank you very much also for inviting me. So yeah, as already explained, I'm Dudek Sebastian, but I'll also introduce a little bit myself. Today I will speak about the introduction to IoT hacking with SDR, and for that subject, I have choose to talk about the LoRa, some LoRa equipment. For example, some LoRa equipment that you will see here. So I will be presenting in live some hacking stuff. So let's begin. So so this is the thing that you already know. So I'm working for Trend Micro for industrial IoT, mobile stuff. I'm the founder of Pentest company. So I'm doing also red team test training and pen testing in hardware and RF and so on. So I will just move on. The agenda of today is to present the specific challenges when it comes to assess the IoT stuff, for example, because we have a lot of challenges when we try to hack some RF communications with some devices. So I will talk about these challenges, and then we will also talk about how to attack them. For example, how to find some vectors of the attack, how to identify the technologies, how to identify also the signal over the air. Then we'll also try to analyze the protocol, interfacing with the RF, and then try to attack it and so on. Try to do some eavesdropping, injection, etc. And also at the end, I will just explain, I will just talk about a little bit about hardware attack with few words. At the end, also, I will just conclude, do a little conclusion, but you will see that generally, also when I will speak about the RF, you will see that also the hardware is quite important while doing assessments and thus in this kind of scenarios. So let's talk first about challenges in RF security. Generally, when you want to assess when you are hired as a security consultant, you begin your assessments. For example, if you do like a network assessment, you begin with one vector, which is like the Ethernet interface. But the problem with the air interface is that you don't see the signal. You don't see any interface how to plug in the signal in order to get something. I mean, for example, if an IoT device is communicating an RF, how you can interface with it? This is the real challenge, because actually it doesn't use any interface, any physical interface that you know already. For example, like the internet connection, some wires, etc. This is like some wire that you don't see. So you will be a little bit struggling with something called like electromagnetic waves. So here is like an example of electromagnetic wave with a linear polarized antenna. So you have to have this kind of antenna, for example, to get this type of technology. I mean, this type of communication. When, for example, an IoT device is communicating with this kind of antenna, you have to use exactly the same antenna in order to capture the energy, to transform it to voltage, and then do the conversion from analogic to digital, and then demodulate, and then also decode the signal, and also do maybe the decryption, because maybe there's some layer of encryption on the communication. The targets at risk are the following. So you have like access controls that you maybe already know. There are also cell phones. There are also navigation systems, autonomous cars. Autonomous cars are pretty amazing, because it is like, you have to imagine that a car is just like a big set of a lot of subsets of computer, and all these computers are communicating with some technology. Some are using Wi-Fi, some are using like custom RF system to do some telemetric stuff. So there are plenty of things that are communicating together. You don't have just the CAN bus, for example, to communicate from one ECU to another ECU. Industrial systems also use communication, and industrial systems use, for example, LoRa, Zigbee, etc. So the risks with the interface are the following. So generally, when you for example, with Wi-Fi, you can, for example, monitor what is going on in the air. So you can do some eavesdropping. You can maybe try to replay a signal. For example, if someone is like just pushing a button, you can just capture the button and then replay the button in order to see if, for example, there is like some replay, anti-replay mechanism. You can also inject signal after, for example, analyzing your signal. You can maybe inject some data that you have forged yourself. You can also relay the communication, for example, that is used, for example, imagine that a lot of stealers use the relay attack against, for example, the cars to do some carjacking. You can also do the jamming attack, DOS attack, etc. So there are like plenty of attacks to test already. And to do this kind of attack, before it was really difficult, because we didn't have like what is called SDR. SDR is called, it is the acronym for software-defined radio. And before, it was very complicated, because you had to have like a specialized device in order to communicate with the device. For example, for the Wi-Fi, you need to at some point have a device which is compatible with this kind of channel in order to communicate with like an access point or any device using Wi-Fi, for example. But with SDR, you have like a flexible way in order to build your own communication on the fly, and already test in already interface, which is like kind of amazing, because, for example, if someone is doing like a custom device with a custom RF communication, with a software-defined radio, you are able to build your own, for example, your own capturing device, and you can, for example, just at the beginning capture the signal, and then try to analyze the signal in order to reverse the signal, to then maybe understand what is going on between two devices. And then you can maybe inject some frames that you have forged yourself, etc. So this is like pretty amazing what you can do with software-defined radio. And the only thing that you need is an hardware. The hardware is used, for example, to do some signal acquisition, translate it to an intermediate frequency. Then you do the decoding, encoding. You pass from analog to digital, or to digital to analog if you want to transmit a signal, for example. And after that, what is done is that the hardware part will just forward all the samples to your computer, because your computer then will be responsible to do all the processing. For example, it will be responsible to do the demodulation, the decoding, the decryption, then on the higher level, etc. So this is pretty amazing. And what is amazing also is that now, from 10 years ago, it wasn't the case. More than 10 years ago, it wasn't the case. But now, with a very cheap SDR device, like for example the RTL SDR, at some points you can, for example, get one RTL SDR for 15 euro, not much. This version costs 50 euro. This version is also very good because actually it supports a lot of frequency ranges. And also what I love with that device is that it has also a metal case that if, for example, if you keep running this device for several hours, you can already, like, see that it's very hot, and you can also hit some eggs and also bacons on it, because actually it is very hot. So, but yeah, it's quite funny. But this device is also very optimized. So this is why also it costs like 50 euro, because you pay also for the price. I mean, you pay the good price for this kind of software. I mean, this kind of SDR device. It's also good for the beginning. Also, if you're new to SDR, you can buy Nadam Pluto, which is also not very expensive because it costs like around 100 euro. It supports a lot of frequency. Also, it supports much more frequency when you overclock it. And it is just like a software overclock that allows you, for example, to set the device from 70 megahertz to 6 gigahertz, which is like amazing. But there is like always a but with this kind of price, is that it uses, like, for example, USB 2 interface, which is like, not very relevant. For example, if you want to to forward an amount of samples at, for example, 61.45 44 megasample per second. So it's not very relevant. But if you are looking for other professional SDR, you may maybe notice on this Wikipedia page that there are like plenty of devices, like 100 devices. So yeah, and what you have to look at is like, does the device is doing TX or RX? Does it like full duplex or half duplex? What is the max sample rate? What is the clock stability? What is the interface, USB 3, PCIe, etc.? What is the frequency range? What is the software support, which is also interesting because you can also waste a lot of time trying to make your hardware device work. So yeah, there are like plenty of questions, and this is like, not a very simple question. When people ask me which SDR I have to buy, I'm always like asking, what is the purpose of your SDR? Because actually you have to know that there are no generic devices that can do everything at once. You can always like buy one that will be very good for your purpose, and with time you will be like me, having plenty of cartoons at your home, and you will not have any places to keep all of this. So actually, you will buy all of them, and you will not have a lot of space. And also, if you, for example, if you live in Paris, you may know that we generally, when we live in Paris, we don't have a lot of place to live in, and you can imagine that it's I can waste a lot of space just buying all the stuff like that. So let's now attacking the RF device. So for the purpose of the attacking, I have choose the LoRa one, the LoRa devices, like one GPS tracker, one dual sensor, one dev kit. So it communicates already, for example, with the Things network backend server, network server. And what you may know about LoRa is that it's it's already used in plenty of purpose. For example, it is used for wireless alarms, for industrial systems, etc. For industrial system, for example, to command one PLC in remote. So actually, it is used in plenty of systems. The existing tools, when it comes to assess the LoRa, this year there was like a really good presentation about IoActive this year about LoRa, which they made like a really great tool, because it was like a very great work by doing it. Because when you see the framework they did, the framework it's like kind of huge. But it has like few limitations. Like, for example, it only works with gateways. It can only listen to uplink packets. He can only listen to 8 out of 64 channels, for example. The generation and the flooding is also not very flexible. So at some points, we had also to make our tools, but we have also saw that there was like another tool called Chiport. if you look at the paper also, it shows you like a very nice wormholes attack using nodes, but still it's kind of limited. So we needed, for example, for our purpose at Trend Micro, but also for myself, I needed to be like as much low level as possible, and I needed to be like as much flexible as possible. So I will just explain what are the steps to attack this kind of the devices, for example, the LoRa devices using SDR. So at the first steps, you have to identify the signal. So we can, for example, use like an RF Explorer in order to see what is happening in the air, and we can see that there's like, for example, communication at the 868.244. There is like a signal which is like sent over the air. The problem with LoRa, you will see, is that also LoRa devices use plenty of frequencies. It doesn't, I mean, many frequencies. It doesn't use like just one central frequency to send some signal. It uses many channels. So actually, the problem with that is that here I can see, for example, one channel, but I will see also other channels if I run the device. I mean, if I run my RF, my RF Signal Explorer a little bit more. In UE, we can actually use like the RF Explorer, but also other RF Explorer that costs like a little bit more. This RF Explorer costs like 300 euros, sorry. But it's a little bit limited, so you can also buy some Pro devices also, but that costs much more money. You can also do that with SDR as well, and for example, using decoders, etc. The identified band, for example, for the LoRa communication are the, as I said, the 868 MHz in UE, in Europe. You can also check out what are the frequencies which are used in other countries. And to identify the signal with the SDR, there are like software that I've already told about, like JQRX, SDR Angel, SDR Sharp, etc. So after identifying your signal, you have to identify also what are the modulation which is used with that device. What is the coding? What is the protocol? Is there some encryption? So this is the kind of question also you have to answer. And there are like many ways to do that, but two main ways to do that. For example, looking at the hardware, for example, with a physical access, or you can also do that in blind with RF. For example, this kind of scenario, the last scenario happens, for example, when you are an attacker, you don't know exactly what you are looking for, you just see like a signal in the air, so you will maybe try to find first the frequency and then try to associate the frequency with some technology that are used. So the blind way is, takes like a lot of time, but so generally also physical access is quite good. So when you have a physical access, what you want to do is like you identify the transceiver chip, which tells you about the use frequency, also the technology, the modulation, etc. So you can just grab the specification of the transceiver and see what are the specifications, so you can have like a better understanding on what is going on. There are also other components that may be like around, so you can also look at this, but the transceiver on the RF side is the primary thing to look at. You can also look at the FCC ID. For example, if your device has an FCC ID, you can look at the FCC ID database in order to see what are the information about this device. And the FCC ID provides you a lot of devices, including some tests, some RF tests, etc. So you can have like already some very good information about what is going on in the air, for example. So now, once you have identified the modulation, you can just guess that LoRa exactly use its own modulation. It uses also the FSK modulation, which is like the frequency shift modulation, but generally it uses this modulation, which is like quite much optimized for this kind of transmission, because it uses the LoRa modulation in order to send a signal very far away. And so for the LoRa modulation, use some chips, and the chips are the composite high intensity radar pulse, which are some sinusoid signal which change in frequency. And there are, as you can see, so the chips looks like that. So you have like some, some sinusoid wave that move in frequency like that. You can have also longer, longer chips. That means that also they use like a split spectrum, which is a little bit longer. So it takes like also a lot of much more time, for example, to send some data, as you may guess. And the two types of chips that you can find, for example, you can find uplink and downlink chips. For the demodulation part, what you have to do is generally you receive your LoRa signal, and then you have to mix this received LoRa signal with some inverse chips in order to get some decoded symbol. And then once you get the decoded symbol, you try also to then to interpret this decoded symbol to some values. So this is like the macro view of that. But if you want, for example, to use SDR, you have to know that you can make there are already some blocks that are already developed for that purpose. And so there are like the RPPI 0 GR LoRa that only does the RX. There is also the GR LoRa from Basti, which does the TX and the RX. So it looks like that. So you have, for example, use your USB source, which will acquire the signal, and then you have like a LoRa receiver that you have to configure with one channel, one spreading factor, and also one bandwidth, which is like which we'll see that's it will be like a little bit painful because you have to know that also LoRa use not one channel but many channels, and it can use also many different splitting factors. So yeah, this is like just a thing right now, but you will see maybe that's just a bit after that. This is also important. So yeah, actually we use GNU Radio Companion in order to design a flow graph, and then we can decode the signal just basically like that, with like just at least two blocks, with the block the block source to acquire a signal, and then another block to decode the signal. But as I said, LoRa use plenty of other splitting factor and also plenty of other bandwidth, but also plenty of channels. So imagine that if you want, for example, to add every channels, every splitting factor in your flow graph, you will just like you will, for example, at least for UE, you will use like at least 80 blocks to support all the channels and all the splitting factor, which is like kind of crazy, because also you have to know that if you, for example, use one block for decoding, you have to know that these blocks will take a lot of time also. They will do the processing, so they will have to take the samples, process the samples, and if you like put like 80 blocks that will do that will do the decoding of LoRa packets, you will introduce a lot of latencies in your flow graph, which is quite not good. So we have to do some optimization first. So to do the optimization, we can use heterodyne, which is like a physical things that we use, for example, in electrical engineering, and also you have maybe used that before when you were studying these kind of things. So you just mix like two signals, which are F1 and F2, for example, and that will produce two other signals, which are the F1 minus F2 and F1 plus F2. So you will produce this kind of signal with that kind of mixing. In IQ, for example, using quadrature signal like that, using a mixer like that, you will produce F1 plus F2. So what we have to do is that we have to just arrange. We have to work with a frequency that will, for example, shift will shift, for example, a signal to a specific frequency. So we will just, for example, for this kind of purpose, and that was also, this kind of purpose was already presented by Tristan Cavli and José Lopez Esteves, which were, for example, they were capturing, for example, 1 megahertz. Here it was like a sample rate of 1 megahertz. Wait a second. Yeah, it was like a separate of 1 megahertz. So they were actually capturing just like a 1 megahertz bandwidth, And with that, they were shifting all the frequency to the center frequency of LoRa, which are the 868 megahertz. And so then, using the heterodyne, they could shift every signal using, for example, one signal source that will shift already some signal that are, for example, at one channel. They will shift it to one center frequency, so to one intermediate frequency, in order to use the LoRa receiver, which with just one frequency, which is the 868 megahertz. And but the problem is that yeah, this implementation is quite interesting, and but it still needs some improvements. So for our purpose, what we did is that we have just took back this concept, and we have implemented it to our own hierarchical block in order to simplify the flow graph that we will use. And so here we are doing exactly the same. So we have a signal source which will do like the shifting from one frequency to the base frequency of LoRa, and also a low pass filter that will also perform the decimation. So here there is like a parameter decimation which is at 1, and which is also interesting is that we were studying also what will be the best decimation in order to, for example, to feed the padsync that will be the LoRa receiver with the minimum sample rates. I mean the minimum sample the minimal samples to process to LoRa receiver. Because, for example, if you take, for example, a lot of samples and you try to process it to the LoRa receiver, the problem is that you will have a lot of latency. And so what we want to do is that we want to optimize, for example, the receiver in order to just give to the receiver the minimum amount of samples in order to do the decoding. And so like that, we can also optimize some decoding, some processing. So this is something that we have done with the decimation. So by calculating the right decimation, we have to know that in the sampling theorem, we have to respect the Nyquist and Shannon sampling theorem. And so you have to know also that LoRa phi has a minimum of 125 kilohertz. So we have to sample at least at 200, at least at 250 kilohertz. But in practice, we have seen that the LoRa receiver only takes an amount of samples with a value of 500 kilohertz. So actually, the sample rate that we have to of our signal that will come to the LoRa receiver will have to be 500 kilohertz to work properly. So the best decimation to use for the low pass filter will be this one, is the decim equal sample rate divided by 125 at the power of 10, multiplied by 10 of the power of 3 divided by 4, and like that we can put everything together. So here, as you can see, we use a sample rate of 2 megahertz for our Osmocom source. That will be the source. For example, the device like RTL SDR. So the RTL SDR will sample at 2 megahertz, and then you see that the decimation will just divide the sample rate by 4 to the LoRa decoder that will be here, and so like that will not sample too much. Will not just forward too much samples to the decoder, and the decoder will not be too slow to process all the samples. And here is the general flow graph we use. So here you can see, for example, just the recenter LoRa channels that we have made here in order to do, for example, the heterodyne. And so like that, just putting an add operation and adding all the signals and using just this amount of decoder that you have to multiply by 2 to get the real value of the real amount of LoRa receiver decoder. You can see that with this flow graph, we are able to decode all the LoRa channels of the European of Europe. So our result is the following, and also I will show you a little demo just after. So decoding the 8 channels, 8 LoRa channels with multi-splitting factor with just like a small, just a very simple, I mean a very simple RTL SDR like that. So we can also do some further optimization because, as I said, we have to process a lot of samples. Each block has also to process these samples. So we can also, for example, instead of using like a sample multiply, we can use, for example, the OpenCL modules. We can use the OpenCL modules in order, for example, to replace the multiply operation with the OpenCL multiply and the OpenCL low pass filter, for example. So to do the decoding part, also because actually we will have like when we will decode all the samples, we'll have just like just a set of bytes that are not very understandable. We cannot understand. So to do the decoding part, we need like a decoder. But at the time, we just like got like very few decoder. So these are the few decoder we had, but we have also made our own decoder, which is based on SCAPI, because SCAPI, give us like the flexibility of regenerating, generating each byte of our LoRa signal, which is quite good because if we use, for example, LoRa packets or LoRa 1 Go, these solutions are very good also, but still. If you do, for example, if you want to do some fudging test on the LoRa stacks, it is not like very flexible to do that, and also not as easy as SCAPI. So we have made our own tool. So the tool is based on LoRaCraft from Penterts, and the features are the following. So I will just I will not enumerate all the features, but I will just show you maybe a little demo. So our tools is able, for example, to you can just launch, for example, the flow graph, and you can see also when launching LoRa feed decode, you can see what is going on. For example, here is like an uplink packet, here is also an uplink packet, and here you can see a downlink packet from the gateway, which is quite good. So let's go for some demos. So first, we have like many targets, so I would just like use that one to do the demonstration. So this is like a dev kit target, which will just send signal in a lot of using like frequency hopping. So we use like the RTL SDR, which is like the cheapest SDR device that you can find in the market. So let's plug it, and then we plug also the target like that. Wait a second, like that. Now, super. And now let's go to decode some signal. So I will also, so now you can see, for example, my flow graph, which is right here. I can build my flow graph, and then I can launch it. So actually, it will just like launch it with the RTL SDR. And you will see that where is so now for example my flow graph, which is right here. Wait a second. So you can see, for example, the packet which are here. And wait a second, because I'm just like, I will just tweak the song a little, like that. Yeah, super. So, because I don't know why I can hear also myself. This is quite weird, but yeah, as you can see, for example, here there's like you can see, for example, just like a waterfall where the samples are sent over the air, and you can see that it uses actually different frequency in order to send a signal. So as you can see here, the flow graph works perfectly well because it can intercept each signal that will send over the air. But we want to decode this signal. So to decode this signal, we can use, for example, this tool. So I would just like wait a second, up. I will also my hands are frozen a little bit, so super. So now we will launch the LoRa feed decode. So we can, for example, we can record the LoRa feed decode is able, for example, wait a second, oh yeah, because also I'm using Python 3. So, whoa. So actually the LoRa decode is able, for example, to output this, the things using a pcap. So I can also, I can capture it as a pcap. So for example, I can use like a test2 pcap like that and capture what is going on. So you will see that here, for example, we have received a packet in an uplink packet, and we can actually decode it, which is quite good. And we can, for example, now, as we have intercepted a packet, we can attack the packet itself. So let's now use LoRa feed decode in interactive mode like that. And so now we can, as it is like just like a SCAPI implementation. It uses SCAPI. We can, for example, read the pcap like that with the pcap. And so we can see, for example, what was going on. We have like a new UDP packet. We can look at the UDP packet, and we can, for example, try to see what is the first just the really first UDP packet, and you can see Ethernet blah blah. But there is also a layer which is LoRa here. So actually, yes, it is like an encapsulated packet like that. And so now, at some point we want to, because here you can see that the packet is encrypted somehow. So we'll do some brute force. So with this tool, I have also I have implemented a function which is capable of brute forcing the keys of this packet. So this function is called brute force data mic, because actually here, where is my mouse? So normally you should see a mic which is here, and the mic, if you look at the specification of LoRa, the mic actually use a key in order to protect the packet, the integrity of the packet. And this key is the same that is used also to actually for this version of LoRa, is the same to, for example, to encrypt the packet, the entire packet, the payload, which is here, not the entire packet, but just the uplink data payload, which is here, which is not very understandable. So let's try now to brute force this packet. So to brute force this packet, I have that brute force data mic 10, which is corresponding to a function which is associated to the LoRa 1.0 version. And so now I will take my packets. So let's take this like that. Okay. And now I have also to precise the key. So the key, I will not precise the key, sorry. Wait a second. I will just arrange like that. Use brute force data mic like that. Yeah. I will packet pkt, and I will precise also a dictionary. The dictionary I use is this one, for example. So edict .lst. Yeah. Like that, yeah. And I have also, wait a second. I will just, because no problem. So I have bytes pkt, and I use this resource like that. And yeah, the dictionary is not found, so let's just see the dictionary a little bit. Resource killing. Okay, so Sorry for that. Normally, should oh. Yeah, no problem. Actually, what I was doing is that I'm just brute forcing the key, which is this one. And so if I use then this key to decrypt the communication, I mean, this packet, I can, for example, use this key in order to decrypt the uplink packets. But yeah, actually we are a little bit running on time. So so I will maybe show this maybe later. I mean, not here, but a little bit later. But the idea is that now we have, for example, brute forced this key, and so we are able to then decrypt the uplink data payload, which is here. So I will also. So you got the idea of that. So we are able to decode the packet and then to decrypt the packet. And so there is like sorry for that. I will just change the screen. And so we have for example, we have begin with the physical layer, which is like the radio, and then we have been able to finish it with the decoding and the decryption. So if we want to inject the frames also, we can also use another, I mean, because we can do only the RX part with the SDR for now. But if we want to send some signal over the air, we can also, like for example, do our capture. We can manipulate our capture and then send it using a macro chip, another device like that, for example, that is capable of doing P2P sending. And yeah, this is actually the result of doing the injection. For example, you can DOS the APB mode. We have also the hardware to complete the assessment. For example, if you want, if you don't have like any, if you, for example, need an algorithm or something like that, something as such, you can, for example, try to interface using like the UAT, the GTAG, the SPI, D2C, etc. And this is like, just an example of how you can interface with a device to them the keys, to them also the firmware logic, etc. So, for example, for the ROA devices, you can, for example, dump the keys using this kind of interface. So the conclusion is the following. So actually, the assessment on the RF like is kindly like the network assessment. So, but it needs a lot of work trying to find the signal. I mean, over the air, trying to see how it's behaving, how what are the specifications, what is the technology, etc. So it takes like a lot of time trying to reverse that because you need to know the modulation. So you have to recognize the modulation, demodulate it, decode it, etc. So it's like a plenty like a lot of work. But at the end, this is like a network assessment at the end. So what is cool with SDR is like it's pretty accessible. You have like a lot of flexibility. It is not as powerful as using like a dedicated device because as you can see, all the samples, for example, are processed by your computer. So if you don't have like, for example, a very powerful computer, it's very difficult to process a big amount of samples. So it's kind of difficult to work with like complex, very complex, communications. And at the end, the hardware is very complementary. So you can, for example, dump the keys, dump the logic of the hardware, etc. So it helps a lot while trying to, for example, do the interception and analyzing your signal. So yeah, that was it. And actually, also, if you're interested about some SDR challenge, don't hesitate to, for example, if you want to do some challenge about SDR, we have also a CTF called, capture the signal, which you can look at this address. There's also a next event about that at HETB Cyber Week. So here is the link. And thank you very much. And if you have any question, please ask. I'm waiting about. I'm open for all your questions. I'm open to all your questions. Mm. Mm. Okay. Yeah, sorry for that. Thank you very much, and thank you for the invitation. It was a pleasure. Bye-bye, and good luck also for our students.